So let us take some preparations and the properties of these phenols. Phenols, a common phenol is an aromatic system like benzene with a OH group, it is called phenol. But any aromatic system with attached OH may be called as a common phenols. Any aromatic system, but directly should be attached OH. And if R attached OH, we call it as an alcohol, right? So a system like, for example, if benzene is there, let maybe a methyl is there, but if OH is there, this is an example for the phenol. Whereas if the OH is there on the carbon which is attached to the benzene, this is an example for alcohol. That means a saturated system, if OH is attached, we are calling alcohols. If OH is attached to directly to the ring of a benzene or naphthalene, naphthol, a naphthalene with one position, second position, let us say OH, this is called beta naphthol. Is also an example of for the phenol. So phenol is a common name for this particular compound. However, it is a phenol means this is a type of phenol, this is a type of phenol. So all the aromatic compounds containing hydroxy together we call them as a commonly phenols. But specifically I want phenol means this is the phenol, just like I want alcohol means what is the alcohol? All are different alcohols are there, but specifically in the market if I want alcohol means ethyl alcohol, that is what the people give to you. If I want alcohol means ethyl alcohol, that is referred as a commonly ethyl alcohol is called as common alcohol. Like that, common phenol is a benzene with OH, that is the simple phenol. However, this is a hydroxy with OH, it is called cresol, it is called para-cresol. It is also an example for phenol. Naphthol is also a phenol. All phenols show common properties. So let us have how the phenols are prepared. So preparation methods for the phenols. There are four common or the commercially feasible methods, important methods are there. All are commercially feasible methods. One is a hydrolysis of phenyl chloride or chlorobenzene. Aliphatic systems that like methyl chloride, ethyl chloride undergo very easily or facile type of the hydrolysis, because the halogen attached to the system like here RX OH minus readily attacks and shows a nucleophilic substitution reaction to give the alcohol. So in the case of alcohol, the reaction happens to be damn easy, because the alkyl halides favorable reaction, that is nucleophilic substitution, X will be going and OH is coming. But whereas in the case of aromatic system, the chlorobenzene, the chlorine happens to be showing a mesomeric effect plus some effect with the benzene, and this double bond nature will be there many times. And the chlorobenzene, as it is showing the resonance, it is stabilized, less reactive. And the nucleophile attacking on the system is also tough job, because it is aromatically electron rich center on that OH is attacking is a partly difficult it is. But the difficulty thing can be achieved by under the three conditions. First one is the high concentration, concentrated NaOH or KOH should be required. Second condition, high temperature. This is a high concentration, high temperature around 350 degrees centigrade is required. This is not really much high temperature, but the pressure is really high pressure, means this pressure is approximately around 150 atmospheric pressure. So, normal pressure is actually 1 atmosphere, but this is really, when compared, it's very high temperature. All these three conditions if you maintain, definitely in the laboratory conditions you cannot go for that high pressure because glass flask will blast out. But you must have a stainless steel or the iron supported the flasks and all that. In such a condition you can do this reaction. This is commercially known as Dow processes. It's a plural actually. You can say Dow process. Under this condition the OH can replace. The concept is, as I said, this chlorobenzene is less reactive towards aromatics nucleophilic substitution. So, somehow you will get this one, but the moment you get the phenol, because highly concentrated, you may have a sodium salt will be the answer. That on dilution with dilute the HCl you will get the phenol. So, this is the one conceptually it is difficult, but still industrially it is possible by going for the high even the conditions exactly you need not to mention, it is a patent actually, but the high concentration, high temperature, high pressure will give the reaction. That is the good concept of this reaction. Impossible reaction made possible, and it is a known name reaction called Dow process reaction. The second possible method is a hydrolysis of diazonium salts. Diazonium salts. Hydrolysis of diazonium salts. Benzene containing a nitrogen with like this will have a positive with the Cl minus, or some other anions also can be there. Originally the nitrogen itself is a minus I group, but because of the positive charge on the nitrogen it will be a very highly better, one of the best outgoing group. So, it requires not much difficulty, just add some water and boil it. Add water and boil it, the group will go and a OH will come. So, in this case the reaction happens to be very, very facile reaction. The only thing is, now in the market the diazonium chloride will not be available. You have to prepare this from the diazotization of the aniline. So, take the aniline and add the nitrous acid. HNO2 is the reagent, however, it is also not available in the market. You have to generate it on the spot by taking NaNO2 and HCl, maintaining at 0 degrees centigrade. This NH2 will become into N2Cl, wherein one nitrogen becoming into two nitrogens. This process is called diazotization. So, one can also prepare in fact from the aniline to phenol. This is aniline. Aminobenzene is commonly known as aniline, that is phenol. So, aniline to phenol, first convert into diazonium salt and then go for the phenol. So, the diazonium salt to phenol is a very simple hydrolysis reaction, just add water, boil it. But getting this compound readily is not possible. You can prepare from the aniline and then go for it. So, therefore, aniline to phenol is a good commercially, the diazonium salts to phenols is a commercially feasible reaction. You can go another commercially feasible method through sulfonation or hydrolysis of sulfonic acid. Sulfonic acids can be prepared from the sulfonation of benzene in turn. So, benzene on concentrated sulfuric acid at around 100 degrees centigrade. Sulfonation is electrophilic substitution. So, benzene has a favorable condition to get this sulfonated product. So, benzene sulfonic acid is prepared then by this hydrolysis reaction. However, just with water you won't get it. You add the concentrated potassium hydroxide and then fuse it. In fact, you can take a solid KOH and a solid this one and fuse it. When you fuse it, the whole group is replaced by the OH group, but in the strong base the OH will be existing in the form of the salt. So, therefore, you will get a phenoxide salt of potassium. Potassium phenoxide will be the resultant, which can be marketed as it is also, because reactions like Riemann-Timer reaction or Kolbe-Schmidt reaction needs a phenol salts, where you can take this one directly continue the Riemann-Timer reaction. So, here this if you want really the phenol means just add some dilute HCl, you will get neutralization, or you can write H3O plus. So, neutralization of phenoxide, you will get the phenol. So, there may be 2-3 steps, but it is commercially feasible. Benzene is commercially sulfonated and then phenol. Even in the last reaction also, aniline really the cost wise it is more cost than the phenol, but it is industrially from benzene nitration, reduction and then diazotization, getting the phenol is commercially feasible reaction. Then lastly, we have one more commercially feasible reaction, that is the oxidation of cumene. Oxidation of cumene. Cumene is a isopropyl benzene, which in turn can be prepared from the again benzene. Benzene by treating with the isopropyl chloride in presence of anhydrous aluminum chloride. Here the concept is here, the aluminum chloride takes the Cl, you will get a carbocation which is a 2 degree and then attacks. You too can take N-propyl chloride even. N-propyl should give the N-propyl, but N-propyl carbocation formed undergoes a rearrangement to give the 2 degree, and then again you will get the isopropyl benzene only. You too can prepare isopropyl benzene from the corresponding alkene taking also. Propene in presence of Lewis acids like BF3, HF and so on also. The anion part that is BF3 attacks here, you will get a carbocation which attacks later and the H replaces. You will get the isopropyl benzene which is called cumene, commercially known as cumene. The cumene has one interesting point. There is one hydrogen on the middle carbon. Notice it. This is a 3 degree hydrogen. If this hydrogen is removed as a plus or minus or a dot, then this corresponding intermediate has got the multi-level stabilization. One is inductive effect. These through methyls will have a electron donating. So, therefore, a carbocation formed on this carbon is stabilized. 6 hyperconjugation, this side 3, 6 hyperconjugation stabilize the carbocation. Benzene shows a plasm effect and then stabilize this one. So, therefore, ultimately original hydrogen is a hyperconjugatable to the benzene, so highly reactive. So, therefore, all this the points will favorable for the hydrolysis of this compound. So, when this cumene is treated with a dilute sodium hydroxide, in presence of this one, pass the air, atmospheric air, pass the air through this one, this oxygen will insert between that 3 degree carbon hydrogen. So, you will get a carbon with OOH. This is called peroxy bond formation. The oxygen is inserted, and because of the high reactivity this is possible. Actually, alkanes will not undergo this type of the hydrogen. When you take this compound and then subsequently with dilute H2SO4, it undergoes a rearrangement known as cumene hydroperoxide rearrangement, is a well known rearrangement. In this rearrangement, in acid proton attacks here, water is removed, the phenyl jumps from this side to that side, and a brief mechanism may be shown, but finally what happens is these 3 carbons with 1 oxygen will become into acetone, and the phenyl with OH will become into phenol. So both the products, if I start with the alkene and the benzene, commercially both are available at a lower cost, and if these two are converted into the cumene by the Fiddlecraft alkylation, followed by oxidation and then the rearrangement with dilute acid, will give the phenol and acetone. Both are very much the industrially useful products. Are cost wise, if you compare with them, they are highly costly compounds, and it is really highly fetching reaction. But there is one rearrangement. What is this? Cumene hydroperoxide giving the phenol is a name reaction or a rearrangement called cumene hydroperoxide rearrangement. We will have a one small glance on that particular rearrangement. Let us have this cumene hydroperoxide, that is the last method of the preparation of phenol. The cumene with as I said, with aerial oxidation, it becomes into a hydroperoxide. If this is hydrogen, it is hydrogen peroxide, but one side cumene is there, the other side hydrogen is there, therefore it is called commonly cumene hydroperoxide. In acidic medium, it becomes into the phenol and the acetone. This reaction is known as what? A cumene hydroperoxide rearrangement. There is one step exactly, that is we will see here. In this reaction mechanism, the step 1 is first the proton will attack on the oxygen. For every step there is a good logic. Why not this oxygen? Means if this proton attacks, the water can be removed. So therefore the protonation takes place on the terminal oxygen. So you will get a compound like this. So oxygen will become O plus, that is called oxonium ion. Now what happens? This lone pair will be withdrawn by the water, and the water will be removed. Now the oxygen, just like in the Baeyer-Villiger oxidation, a single oxygen will get a positive charge. So that is highly not a stable one. So one of the group out of the 3 groups, as per in the penacol-penaclone rearrangement, phenyl group is the better one. So the phenyl migrates onto this electron deficient oxygen. This simultaneously you can accept. Moreover, the moment phenyl is removed, you will get a carbocation. Onto that, this water molecule will go. So exactly what is happening is, the water goes to the carbon, the phenyl comes here. There is an exchange. This is actually the step of the rearrangement step. That group goes this side, phenyl will come here. So therefore, the water molecule will be coming here with, however, the plus charge, and the phenyl group will migrate. There is an exchange, simultaneous exchange. No one is detached system, intermolecular rearrangement taking place. And then now from here the one H plus will be detached, and the 2 electrons will be taken by the oxygen will become neutral. However, this H plus will transfer to the oxygen. What is the benefit you get? Means here the carbocation is attached to the saturated carbon, the oxygen plus oxonium ion. If the proton comes here, the oxonium ion will be, now it is closer to the phenyl, which is more I think stabilized, because there is an electron density in the phenyl ring stabilizes. So now this is more stable than this. Therefore from here to here, just a H plus shift of H plus. Then here the 2 electrons will be withdrawn and the proton is detached, and then these 2 electrons are accepted by the oxygen, and then this will be detached. So it will become into 3 pieces. The hydrogen will become proton, this oxygen with this methyl propyl will become acetone, and the phenyl will be detached with these 2 electrons, it will become into the phenol. So finally that leads to give the 3 pieces. One is H plus, the one is the acetone, and the other one is phenol. So this type of the conversion of a hydrogen, that is cumene hydroperoxide, into the phenol and acetone, involving a space step exactly this here the exact rearrangement is involved, but all this shuffling of protons and all that also comes under the rearrangement only. So, finally, that giving a phenol and acetone is happens to be one of the good rearrangement known as cumene hydroperoxide rearrangement, or commonly known as CHPR also. Short form you can make it as a short form, and remember, try to remember as a CHPR, it is cumene hydroperoxide rearrangement. Will have a similarity with the Baeyer-Villiger oxidation, wherein the ketones with trifluoroperoacetic acid follows through this type of the oxygen plus and jumping of the groups, and finally it becomes into an ester. So, we have a similarity between these two with a oxygen electron deficient center on the oxygen, and then the groups are migrating.